Now, as we progress in trigonometry, we're going to see a couple of angles that pop up over and over and over again. One such angle is a 45-degree angle. And we can get a 45-degree angle by drawing a right triangle where the lengths are both 1 as a base unit, and then using a Pythagoras theorem, we can get the hypotenuse. In this case, it's a square root of 2. Now, notice in this triangle that one angle is 45, the other one's 90, the remaining one is 45 as well. So this just happens to be an isosceles triangle. So these pop up often. So if we have something that's measuring 45 degrees, or maybe it's written as pi-4 radians, can we find the trigonometric functions of those particular values, either in degree world or, as we're going to get more practice, in a radian world? So if I wanted to find the sine of 45 degrees, the sine of 45 would equal, remember what sine was? Opposite over hypotenuse, which is 1 over root 2. To rationalize the denominator on that one, I need to multiply both sides by root 2 over root 2. And my final result is root 2 over a 2. So the sine of 45 degrees, or the sine of pi-4, is root 2 over 2. The cosine of 45 degrees, likewise, in this particular case, it's adjacent over hypotenuse. Notice that I have the same process, so that also will work its way down to root 2 over 2. And the last one is the tangent of 45 degrees, or the tangent of pi-4. That's opposite over adjacent, which equals a 1. So looking at this again, this is just a special angle. 45 degrees occurs frequently. So much so that after a while, when you see sine of 45 degrees, you're not going to have to calculate it. You're going to know it's a value of root 2 over 2. Or the tangent of 45 degrees. The ratio of one side versus the other side, since these sides are the same length, their ratio to each other is just a 1. So let's look at another special triangle that produces two special angles. So the other two angles, it's a 30-degree angle and a 60-degree angle. So what I constructed is I constructed a 30-60 triangle. To find the sides, how we kind of do it is I built an equilateral triangle where every side is 2, then put the altitude down the middle and took half of that triangle. So half of 60 degrees is 30, which gave me to 30 degrees. The other angle is 60, and so forth. So I use a little bit of geometry there to build a 30-60 triangle for the purposes of then determining what the lengths of those sides are. Now I have one base is 1, another base is root 3, and the hypotenuse is 2. Those are the values on the standard basic 30-60 degree triangle. So let's experiment with that. Let's look at what the sine of 60 degrees are, or the sine of 60 degrees. Sine is opposite over hypotenuse. Opposite over hypotenuse. This is my 60 degrees, so my opposite is root 3 over the hypotenuse is a 2. The sine of 30 degrees, I changed my angle. My angle's up there now. So the opposite of that particular angle, the side, is a 1 over a 2. The cosine, let's look at cosine of 60 degrees. Back at the 60-degree angle, the cosine is the adjacent over the hypotenuse, which is a 1 over a 2. And then let's look at the cosine of 30 degrees, just for comparison's sake. Cosine of 30, which is adjacent, which is a root 3 over my hypotenuse, which is a root 3 over a 2. And so that's how you can find the sine and cosines of the other two special angles, 30 degrees and 60 degrees. And if we can find these, we can find the cotangent, cosecant, secant, and tangents just as well. But that's just enough to let you get a sense of, we have three special angles that we'll spend a lot of time around. 45 degrees, 60 degrees, and 30 degrees. And because of that, we're going to start to see these values over and over and over and over again to the point that they become second nature, where we almost don't have to memorize them anymore because we use them all the time.